1.5. The electron. Cathode rays. 19th century physicists didn't just spend a lot of time coming up with wild, random speculations about things like atoms being made out of knots. They also spent a lot of time trying to come up with wild, random ways to play with electricity. The best experiments of this kind were the ones that made big sparks or pretty colors of light. One such parlor trick was the cathode ray. To produce it, you first had to hire a good gas blower and find a good vacuum pump. The gas blower would create a hollow tube and embed two pieces of metal in it, called the electrodes, which were connected to the outside via metal wires passing through the glass. Before letting him seal up the whole tube, you would hook it up to a vacuum pump and spend several hours huffing and puffing away at the pump's hand crank to get a good vacuum inside. Then, while you were still pumping on the tube, the glass blower would melt the glass and seal the whole thing shut. Finally, you would put a large amount of positive charge on one wire and a large amount of negative charge on the other. Metals have the property of letting charge move through them easily, so the charge deposited on one of the wires would quickly spread out because of the repulsion of each part of it for every other part. This spreading out process would result in nearly all the charge ending up in the electrodes, where there is more room to spread out than there is in the wire. For obscure historical reasons, a negative electrode is called a cathode, and a positive one is an anode. Now, before we go too far, there's a nice picture here with a cathode ray. Light emitted when cathode rays hit air molecules. Light emitted when cathode rays hit the glass. The figure shows the light emitting stream that was observed. If, as shown in this figure, a hole was made in the anode, the beam would extend on through the hole until it hit the glass. Drilling a hole in the cathode, however, would not result in any beam coming out on the left side, and this indicated that the stuff, whatever it was, coming from the cathode. The rays were therefore christened cathode rays. The terminology is still used today in the term cathode ray tube, or CRT, for the picture tube of a TV or a computer monitor. Were cathode rays a form of light or of matter? Were cathode rays a form of light or of matter? At first, no one really cared what they were, but as their scientific importance became more apparent, the light versus matter issue turned into a controversy along nationalistic lines, with the Germans advocating light and the English holding out for matter. The supporters of the material interpretation imagined the rays as consisting of a stream of atoms ripped from the substance of the cathode. One of our defining characteristics of matter is that material objects cannot pass through each other. Experiments showed that cathode rays could penetrate at least some small thickness of matter, such as a metal foil of a tenth of a millimeter thick, implying that they were a form of light. Other experiments, however, pointed to the contrary conclusion. Light is a wave phenomenon, and one distinguishing property of waves is demonstrated by speaking into one end of the paper towel roll. The sound waves do not emerge from the other end of the tube. The sound waves do not emerge from the other end of the tube as a focused beam. Instead, they begin spreading out in all directions as soon as they emerge. This shows that waves do not necessarily travel in straight lines. If a piece of metal foil in the shape of a star or a cross was placed in the way of the cathode ray, then a shadow of the same shape would appear on the glass, showing that the rays traveled in straight lines. This straight line motion suggested that they were a stream of small particles of matter. These observations were inconclusive, so what was really needed was a determination of whether the rays had mass and weight. The trouble was that cathode rays could not simply be collected in a cup and put on a scale. When the cathode ray tube is in operation, one does not observe any loss of material from the cathode, or any crust being deposited on the anode. Nobody could think of a good way to weigh cathode rays, so the next most obvious way of settling the light-matter debate was to check whether the cathode rays possessed electrical charge. Light was known to be uncharged. If the cathode rays carried charge, they were definitely matter and not light, and they were presumably being made to jump the gap by the simultaneous repulsion of the negative charge in the cathode and attraction of the positive charge in the anode. The rays would overshoot the anode because of their momentum. Although electrically charged particles do not normally leap across a gap of vacuum, very large amounts of charge were being used, so the forces were unusually intense. Thomson's experiments, and there's a picture of him here. Physicist J.J. Thomson at Cambridge carried out a series of definitive experiments on cathode rays around the year 1897. By turning them slightly off course with electrical forces, as shown in the figure, he showed that they were indeed electrically charged, which was strong evidence that they were material. Not only that, but he proved that they had mass and measured the ratio of their mass to their charge, m divided by q. Since their mass was not zero, he concluded that they were a form of matter and presumably made up of a stream of microscopic negatively charged particles. When Millikan published his results 14 years later, it was reasonable to assume that the charge of one such particle equaled -1 fundamental charge. Q equals -e, and from the combination of Thomson's and Millikan's results, one could therefore determine the mass of a single cathode ray particle. And I'm going to read this caption here below. Might be a bit out of order. Thomson's experiment proving cathode rays had electric charge, redrawn from his original paper. The cathode C and anode A are as in any cathode ray tube. The rays pass through a slit in the anode, and a second slit, B, is interposed in order to make the beam thinner and eliminate rays that were not going straight. Charging plates D and E shows that cathode rays have charge. They are attracted toward the positive plate D and repelled by the negative plate E. Okay, continuing the reading. The basic technique for determining m divided by q was simply to measure the angle through which the charged plates bent the beam. The electric force acting on a cathode ray particle while it was between the plates would be proportional to its charge. And you can see the equations. And application of Newton's second law would allow m divided by q to be determined. Okay, just going to read it here. There was just one catch. Thomson needed to know the cathode ray particle's velocity in order to figure out their acceleration. At that point, however, nobody had even an educated guess as to the speed of the cathode rays produced in a given vacuum tube. The beam appeared to leap across the vacuum tube practically instantaneously, so it was no simple matter of timing it with a stopwatch. Thomson's clever solution was to observe the effect of both electric and magnetic forces on the beam. The magnetic force exerted by a particular magnet would depend on both the cathode ray's charge and its velocity. Another equation. Thomson played with the electric and magnetic forces until either one would produce an equal effect on the beam, allowing him to solve for the velocity. Knowing the velocity, which was on the order of 10% of the speed of light for his setup, he was able to find the acceleration and thus the mass-to-charge ratio. Thomson's techniques were relatively crude, or perhaps, more charitably, we could say that they stretched the state of the art of the time. So with various methods he came up with the m divided by q values that ranged over about a factor of 2, even for cathode rays extracted from a cathode made of a single material. The best modern value is, as you can see, which is consistent with the low end of Thomson's range. Okay, next page, end of the section. The cathode ray as a subatomic particle, the electron. What was significant about Thomson's experiment was not the actual numerical value of m divided by q, however, so much as the fact that, combined with Millikan's value of the fundamental charge, it gave a mass for the cathode ray particles that was thousands of times smaller than the mass of even the lightest atoms. Even without Millikan's results, which were 14 years in the future, Thomson recognized that the cathode's ray m divided by q was thousands of times smaller than the m divided by q ratios that had been measured for electrically charged atoms in chemical solutions. He correctly interpreted this as evidence that the cathode rays were smaller building blocks. He called them electrons, out of which atoms were formed. This was an extremely radical claim, coming at the time when atoms had not yet been proven to exist. Even those who used the word atom often considered them no more than mathematical abstractions, not literal objects. The idea of searching for the structure inside of unsplittable atoms was seen by some as lunacy, but within 10 years Thomson's idea had been amply verified by many more detailed experiments. And there are many discussion questions here, which I suppose I will omit reading, but are visible for the reader.